Welcome to the Chemical Glycosylation module of the Carbohydrate Chemistry stream of resources. My name is Ryan Snatinsky, and I am GlycoNet's Training and Project Management Coordinator. In this module, we will discuss how to attach sugars to other molecules chemically. The topics we will address include a definition of glycosylation, followed by a discussion of the role of each component in a glycosylation reaction, with a particular emphasis on donors and the factors that influence their reactivity. We will then apply this knowledge to describe how to make specific linkages, and finish with an introduction to the concept of orthogonal glycosylation. If you are looking for an introduction to the biological synthesis of carbohydrates, be sure to check out the video module on enzymes and chemoenzymatic synthesis. Glycosylation is the attachment of a sugar to another molecule. In biology, this linkage is usually through an oxygen or nitrogen atom, and the attached molecule could be a protein, lipid, nitrogenous base, or another carbohydrate. The earliest synthetic glycosylations were developed by Emil Fischer, who went on to win the Nobel Prize in 1902. In a Fischer glycosylation, the unprotected sugar is suspended in an alcohol and treated with an acid catalyst to produce an equilibrium mixture of pyranose and furanose isomers. The exact isomeric ratios depend upon the nature of the sugar, alcohol, and the reaction conditions. This method is not practical for attaching sugars to anything beyond simple alcohols, and in modern times, more reliable glycosylation methods have been developed. Glycosylation reactions require two components, a donor and an acceptor. The donor is the sugar molecule that will determine the type of anomer present in the resulting glycoside, while the acceptor contains the nucleophile that attacks the donor during the course of the reaction. The majority of modern glycosylation methods activate the donor sugar in some way to form an electrophilic oxocarbenium ion intermediate, and it is these types of glycosylations that we will be focusing on in this module. Although we often draw these intermediates as naked oxocarbenium ions, they almost certainly exist in complexation with stabilizing counterions. Many different types of donors have been developed, and we will discuss a few of the more common ones in the next few slides. Glycosyl halides were one of the first types of donor to be developed. Bromides and chlorides have seen the most use, and can be activated using silver or mercury salts. Iodides and fluorides are also known. Iodides are the most reactive and may not even need to be activated. Fluoride donors are the most stable to hydrolysis and can often withstand column chromatography. Thioglycosides are another class of donor. They are easily prepared, hydrolytically stable, and can be stored for extended periods of time. They are activated by a wide range of electrophilic thiophiles. Thioglycosides can also be oxidized into sulfoxides and activated with trifluoromethane sulfonic anhydride at temperatures as low as minus 100 degrees Celsius. Glycosylation using sulfoxides is the gentlest method currently known. Trichloroacidimidates are a third class of versatile and commonly used donors. They can be activated by Lewis acids, such as TMS triflate and boron trifluoride diethyl etherate. Trichloroacetamide is released during the reaction, which may react with electrophilic intermediates to give glycosyl amide byproducts. Trichloroacidimidates are prepared by reacting the reducing sugar with trichloroacetonitrile under basic conditions. Depending upon the base used, different anomers can be obtained. Many other types of donors are known, including acetates, pentenyl glycosides, selenoglycosides, and glycolipoxides. Although used less often than thioglycosides and trichloroacidimidates, these donors can be useful alternatives when molecules are sensitive to certain reaction conditions. Because they are all activated in different ways, these donors are useful when planning orthogonal glycosylations. We will discuss this concept towards the end of this module. The choice of protecting groups on a donor or acceptor molecule can greatly influence its reactivity. This concept is discussed in the protecting groups module. The formation of the oxycarbenium ion is usually the rate-limiting step in any glycosylation. Electron-withdrawing protecting groups pull electron density from the reaction center through induction, destabilizing the positively charged oxycarbenium ion intermediate and slowing down the overall reaction rate. Such donors are said to be disarmed. By contrast, alkyl protecting groups are electron donating and add electron density to the reaction center. This stabilizes the oxycarbenium ion and allows the reaction to proceed at a faster rate. These donors are said to be armed. Sialoprotecting groups add so much electron density that donors containing them are said to be superarmed and react extremely quickly. Modifications to the ring will also have an effect on reactivity. Deoxygenation increases electron density and speeds up reaction rates, while azides are electron withdrawing and slow down reaction rates. Cyclic acetal protection will also slow down the rate of reaction as it prevents the ring from flattening during oxycarbenium ion formation. Remember that the ring oxygen and C1 will have some sp2 character in this intermediate. Many of the factors affecting donor reactivity can be applied to acceptors as well. Remember that acceptors are molecules that contain the nucleophile that attacks the oxycarbenium ion during a glycosylation. Electron withdrawing groups attached to the ring will decrease its overall nucleophilicity, while electron donating groups will increase it. Steric effects also play a role. Bulky protecting groups next to the nucleophile will slow down the reaction. As well, the alcohol at C4 in pyranosides is typically the least reactive, due in part to steric clash from the adjacent hydroxymethyl group. Glycosylations are most often carried out in a moderately polar aprotic solvent, which helps to stabilize charged intermediates. The choice of solvent can affect the selectivity of the reaction. For instance, using an ether as the solvent or as a co-solvent will promote axial selectivity, while acetonitrile promotes equatorial selectivity. Acetonitrile is believed to form an axial nitrillium ion intermediate, forcing the incoming nucleophile to approach from the opposite face to generate an equatorial glycoside. This effect has been exploited in the synthesis of sialosides, which we will discuss near the end of this module. We have now looked at each reaction component and studied the factors affecting them. The last part of this module will examine applications of these methods to synthesize each of the 4 basic types of linkages. These linkages are 1,2-trans alpha, 1,2-trans beta, 1,2-cis alpha, and 1,2-cis beta. Trans linkages, either alpha or beta, are relatively straightforward to make. Acyl oxy groups on carbon 2 can participate in the reaction and direct incoming nucleophiles to approach from the opposing face. Keeping the reaction mixture mildly acidic is extremely important, as large amounts of orthoester can form under neutral or basic conditions. Orthoesters formed from thioglycosides or trichloroacidimidates will usually rearrange to give the desired product. If the reaction is too acidic, it will promote anomerization to the glycoside favored by the anomeric effect. 1,2-cis-alpha linkages are more challenging to make than trans linkages and require the use of a non-participatory group at carbon 2. During activation, the anionic component of the activator, such as bromide or triflate, will covalently and reversibly attach to the donor as a mixture of alpha and beta anomers. Due to the anomeric effect, the alpha anomers are more stable and less reactive, and so the beta anomers will react more quickly with an acceptor. Nucleophilic attack on the beta anomer then leads to the desired 1,2-cis-alpha linkage. These pathways compete with direct interactions between the activated donor and acceptor, with some preference for the product formed by the anomeric effect. 1,2-cis-beta linkages are the most difficult linkages to prepare. Not only are non-participatory groups required at C2, but the anomeric effect is working against the desired product. Currently, the best protocol is one developed by Kreitsch and coworkers. In this method, activation of a sulfoxide leads to an oxocarbenium ion that is in equilibrium with the alpha triflate. Addition of the alcohol then results in an SN2 displacement of the triflate and formation of the desired beta monoxide. The triflate must be added first, or else the alcohol will compete with the triflate for the alpha position in the equilibrium step. The benzylidene bridging the oxygens on C4 and C6 is required for good stereo control. Sialosides present even greater challenges to prepare synthetically than the hexoses for several reasons. First, the anomeric effect prefers the beta anomer, but it is the alpha glycoside that appears most often in nature. Sialosides also feature a sterically hindered tertiary reaction center, which is adjacent to a carboxylic acid that disfavors the buildup of charge on C2. Lastly, there is no directing group on C3. Several strategies have been developed to preferentially synthesize the alpha anomer, and we will highlight two of the most successful. One strategy is to use a thioglycoside donor in acetonitrile, which is believed to form a beta-nitrillium ion intermediate as described earlier. The incoming nucleophile displaces this ion in an SN2 type of reaction to form the desired alpha linkage. A second strategy is to bridge O4 and N5 using a cyclic protecting group. The origin of this effect is unclear, but it has been successfully applied to a wide range of sialolations. Although significant advances have been made in the chemical synthesis of sialosides, very powerful chemoenzymatic approaches have been developed and are in many cases superior. Before we wrap up this module, we will briefly discuss strategies for the synthesis of oligosaccharides. One approach is to build the molecule up linearly from the reducing end, adding each sugar unit in sequence. In many cases, a more efficient protocol is to create building blocks of 2 or more sugars and then attach these blocks together. For this strategy to work, it is necessary to activate one donor individually in the presence of another, which is a concept known as orthogonal glycosylation. As an example, in the diagram on the right, donor X is activated in the presence of donor Y. When planning a synthesis, it is also necessary to ensure that your activation methods won't affect any protecting groups present on any component of the reaction, and that the activation methods don't involve harsh acidic conditions that could cleave glycosidic bonds. This brings us to the end of the chemical glycosylation module. In this module, we've discussed the definition of glycosylation and the role of donors, acceptors, solvent, and the factors influencing their reactivity. We then apply this knowledge to describe how to make specific linkages, and briefly touched on the concept of orthogonal glycosylation. Now that you are knowledgeable about the chemical synthesis of oligosaccharides, we encourage you to continue on to the enzymes and chemoenzymatic synthesis module to learn more about the biological synthesis of these molecules.